Now, problem number 8.183 of Bonac and Sontag. A piston and cylinder assembly contain 2 kg of water at liquid water at 20 degrees centigrade and 100 kPa, and it is now heated to 300 degrees centigrade by source at 500 degrees centigrade. The pressure of 1 megapascal will lift the piston off the lower stop. Find the final volume, work done, the heat transfer, and the total entropy generation. So if you can look at the question itself, it says like the piston and cylinder, which is initially at 20 degrees centigrade, there would be heat transfer. So it make like heat transfer to the system. So it is actually gone up to 300 degrees centigrade. But till 100 kPa, the volume of the piston remain constant. As I say, like when the pressure is this much, then it will be lifted from the stop. So that means like once the pressure is less than 1000 kPa, the volume would remain constant. So what I'm saying, like it will be a problem like we have got a volume, initial volume, and let it be, I'm drawing our battery over here. So we will be having initial volume somewhere. Now we will supply, sorry, we will actually have the pressure increase. So once the pressure reach at 1000 kPa, so then the volume would actually move. So that means like we are moving from volume V1 to volume V1A, let's say, or let's say V1A, or from one state to 1A state. Now once we have reached 100,000 kPa, then when we supply heat to the system, it will actually move from 20 degrees centigrade, whatever the temperature was here, over here, it will move from this temperature towards this temperature, and let it be like this is state 3. So we have got 3 state over here. One is when we have got 20 degrees centigrade and 100 kPa. The second state is when we have got 1000 kilopascal while the volume remain as V1, and then we have got the heat transfer or the change in the volume actually when we are moving from this direction towards this direction, and it will end at 300 degrees centigrade. So we need to find the final volume. Obviously we need to find the work done, and the work done will be only possible from this point to this point, and we have to find out the heat transfer and the total entropy generation. So we have got two volume as two pressure. One is the pressure when the it is still there and the volume is constant, and in which case the volume V would be equal to V1. Obviously V1 is over here and also V1 is over here, uh, and that is mean like the pressure would be less than the pressure which is lifting. And then we have got the pressure which is actually greater, and that is actually 1000 kilopascal. And then the volume, this volume will move from this volume towards the this volume, which means like volume V1A towards the volume V3, something like this. So or V3 or V2, whatever we call it at the end. So let's move towards the first thing first. So we need to find each and every possible property at each and every state. So volume V1 would be equal to the total volume V1, sorry, using this table at 20 degrees centigrade and 100 kilopascal. So let me check, like at 20 degrees centigrade, we would be having, sorry, at 20 degrees centigrade, let me check like what would be the pressure. So moving towards the steam table. So at 20 degrees centigrade, the pressure is 2.339, and our given pressure is 100 kPa. So that means like we are in a compressed region. So 20 degrees centigrade and 100 kPa will be somewhere in a compressed region, and moving towards the compressed region. So yes, at table number B14, at 20 degrees centigrade, and the pressure was 100 kilopascal. That's a superheated, as a compressed region. So obviously there is no 100 kilopascal over here. So there is no 100 kilopascal over here. So 20 degrees centigrade, we do not have got 100 kilopascal. And obviously, as I've already said in the lecture, like if you do not have got any value at that temperature or pressure in a compressed region, you can say simply use the property of the saturated liquid. So we will go to the table, which is actually table B11, and at 20 degrees centigrade, we will be using the property at uh, of the saturated region. So I've moved to already B11 over here. So you just check the at 20 degrees centigrade, we have got the property of the liquid, which is actually 0.001002, and a property at the uh, internal energy of the liquid is 83.94. And yes, moving towards the entropy as well. So we'll find the entropy over here, which is actually entropy of the liquid at 20 degrees centigrade is 0.2966. So this is the problem when you do not have got the any value uh, in a steam table, uh, and that so you can use safely. I'm not saying like safely use. You can use the property of the liquid if you are in a compressed region. So we have got from the table. It was in a compressed region, but we have got the property from the table, which was V1 is equal to 0.001002, and the internal energy is 83.94, and obviously the entropy S1, sorry, it's written wrong over here. So entropy is 0.2966. The volume, total volume is equal to mass multiplied by this one. So the total volume is actually now equal to 0.002. Now we move towards the another state. Now that's the state number one, when we have got the volume which was initially somewhere here, and that is state number one, when the pressure was 100 kPa and the temperature was 20 degrees centigrade. Moving towards the 1000 kilopascal now, the volume V1 would be equal to zero. Sorry, the volume V1 would be equal to volume V1A, which actually mean like the at 1000 kilopascal, we would be the volume would remain constant. Now, if you check the at 1000 kilopascal pressure and checking the value of Vf actually. So let me check the value of Vf in the steam table at 1000 kilopascal. So 1000 kilopascal, the liquid volume is equal to 0.001127, while we have computed like the volume V1 was equal to 0.001002. So our volume is the less than the volume of the volume Vf. So that means like we are still in a compressed region. So at the compressed region, the volume Vf would be greater than the our volume, which is actually so now Vf is equal to 0.0011 something, and that was our volume is 0.001002. So that means like our volume is less than the volume Vf. So we are in still in a compressed region. So now if we heat it like so, the pressure would remain constant while the temperature will go up to 300 degrees centigrade. Now going back to the steam table, and I've already checked like at the steam table at 100 at 1000 kilopascal, 1000 kilopascal, our temperature saturation temperature is 179.91. So that mean like that mean like at 300 degrees centigrade, it will be in a superheated region. Using the superheated steam table, we can find the volume V2, U2, and S2. using 1 megapascal and 300 degrees centigrade. Let me go to the steam table again and let me find out like the at superheated, which is actually B13 now. At superheated region, the pressure is 1000 kilopascal and the temperature is 300 degrees centigrade. So we can use this value. So at this point actually we have got the volume, we have got the internal energy, we have got the enthalpy, and we have got the entropy over here. So we have got volume, internal energy, enthalpy, and S over here. So just putting these value or just copying these value over here. So we have got at V2 we have got the volume, we have got the internal energy, and we have got the entropy over here. So and obviously the volume V2 would be the mass multiplied by this specific volume, and the total volume would be over here. So using the work equation, work done would be equal to pressure multiplied by the change in the volume, and that is 1000 kilopascal multiplied by the change in the volume, which actually we have already from here, minus this one, and you can find the work done, which is actually work done from state 1 to 2. I've already discussed like there won't be any work done over here. The only work done would be equal to from here to here, and I just call it as state number 3, but it was state number 2. Now the heat transfer would be equal to the change in internal energy per work done. We have already got the heat transfer. We have already got the total work done. So we have already got the internal energy, and we have already got the work done. So internal energy change plus the work done, just put the value and you will get the heat transfer as 5932 kilojoule. The as discussed, the total entropy generation will be equal to the total entropy minus the entropy of the system. So the total entropy change, we have already got the S2 and S1 minus the entropy of the system, which was Q. We have already got Q from here, which is this one. We have already got the source temperature. Let me check the source temperature, which is 500 degrees centigrade over here. So this Q minus divided by the source temperature, we can get the entropy generation, which is 5.998 kilojoule per kg. And so the entropy of the system and surrounding is actually greater than the zero. Moving towards the another problem number 8.124 from the Bonac and Sontag, the book you have got at 7th edition. A cylinder fitted with a movable piston contains water at 3 megapascal 50% quality, at which point the volume is 20, the total volume is 20 liter. The water now expand to 1.2 megapascal as a result of receiving heat, which is 600 kilojoule from the large source, which is actually placed at 300 degrees centigrade. It is claimed that the water does 124 kilojoule of work during this process, and it's a like, is the process possible or not? Now if we have got the entropy, final entropy generated, which if it is greater than zero, the process would be possible. If the total entropy generated or the total entropy of the system and surrounding actually is less than zero, so that mean like the process is not possible. So this is a problem of the water again. So state number 1 is actually at 3 megapascal and 50% quality. So that means like we are inside the vapor dome, and inside the vapor dome we have got the value which would be actually of the saturated liquid. So at 3 megapascal, X is 0.5. So using the table, which is B12. So at 3 megapascal, which is 3000 kilopascal, the temperature is 200 and saturation temperature is 3.90. The volume VF is 0.001216. Volume VFG is this one, which is 0.06546. Internal energy of the liquid is 1004 4.76, and the internal energy of the evaporation of is 1599.34. Again, you can just use the other one as well. So at 3000 degrees centigrade, sorry, 3000 megapascal, we have got the enthalpy value over here, and we have got the entropy value, which is actually 2.6456 and 3.5412. So moving back to the problem and putting these value in the problem. So we have got value of Vf, value of Uf, value of Vfg, and value of Ufg over here. Yes, we can use also, you can find the value of, yes, Sfg as well. So putting all these value, we can find the value of V1 as this much. We have got the value of U1, which is this one, and we have got the value of S1 and entropy, which is 4.4162. Uh, you can find the mass by using the formula. The total volume is already been given over here, and the specific volume we have already got at state 1. So the total volume divided by the specific volume would be equal to the mass, which is actually 0.589. So from the first law, it say like, yes, using the first law, it say like the total internal energy change would be heat transfer minus work done. So heat transfer already been given, which is actually, it's say like the as a result of receiving heat. So the receiving heat would be positive. It is claimed that the water does work, which also be positive. So we have got the positive work done and positive heat supplied over here. So the internal energy from the above equation, if we have put the value in here, so the internal energy would be, sorry, U2 would be equal to mass M2, sorry, MU1, and obviously 600 minus 124 divided by that value. So you can get the value, which is actually 2612.6 kilojoule per kg. Uh, Going towards the next pressure, which is 1.2 megapascal, and the internal energy is, now we have got the second state, which is the internal energy. We have got 2612.6 kilojoule per kg. Using the table, saturated table again, and let me check like in a saturated table, let me find out the value of Vf and, sorry, Uf and Ug. So if my value U2 is less than UF, so I'm in a compressed region. If my value is greater than UG, actually, so I'm in a superheated region. So let me check like at state, at the pressure 1.2 megapascal. So at 1.2 megapascal, sorry, I have to go to the saturated steam table. So 1.2 megapascal is not being given over here. So it is either 1.0 or 1.5, but let me check like at 1.0 and even 1.5, the value of UF and UG is given. So UF is 29.29 and 54.70. Anyway, my value is greater than this one. UG is 2384 and UG over here is 2393. So that mean like I'm lying somewhere between 2300, if even if I'm interpolating between 1.2. So moving towards my own value is 2612, not 2300 something. So I would be in a superheated region. So it is 2612.6. Now moving towards table number B13, which is superheated region, and the pressure is 1.2 megapascal. So at superheated region, let me put it over here. At superheated region at 1.2, this is my superheated table, and the pressure is 1.2 megapascal. That would be 1200 kilopascal if I'm saying. So at 1200 kilopascal, and the temperature of, uh, let me check what was the temperature. Sorry, at 1.2 megapascal, sorry, I've got the other value, which is internal energy. So at 1.2 megapascal, I have to check the value which actually coincide with this value, which is 2612.6. So 1.2 megapascal. Let me find out the internal energy, and internal energy is my this value. Yes, so I've got anyway. So 2612.74 is already there. So and that is corresponding to uh, temperature of 200 degrees centigrade. Now, so at 1.2 megapascal, 2612.74, I've got the temperature of superheat, which is 200 degrees centigrade. I've got the volume, which is 0.16930, and I've got the entropy, which is 6.5898 actually. So moving back to the question, temperature is this one, and entropy is this one. So the net entropy would be equal to the total entropy minus entropy of the system. So that's mean like if it is like entropy generation, as we have already said. So the S2 minus S1, I've already got the value of S2. I have got the value of S1 from the previous over here. So that means S2 minus S1 would be there, multiplied by the mass if I'm looking at the total entropy change. QCV is already been given, which is actually equal to 600 kilojoule. The temperature is there, which is, let me check, like the temperature from the large source, which is 300 degrees centigrade, and the other thing is not there. So that means like 300 degrees centigrade is there. So 300 plus 273, that would be the temperature in Kelvin. So my entropy, net entropy, or the entropy generation is 0.2335 kilojoule per kg. That mean like it is greater than zero. So the process which is actually was required is yes possible. So it is possible to expand the water from 3 megapascal 50% quality to a pressure of 1.2 megapascal while generating work done of 120 kilojoule and the receiving heat of 600 kilojoule. Thank you very much. Have a nice time.